We've seen a number of different ways this semester of proving that some property holds for all of the natural numbers. Most recently, we talked about smallest counterexample proofs. Today, I want to extend the idea of smallest counterexample proofs to give us what will be our most useful tool for proving this sort of theorem about natural numbers. If we think about our smallest counterexample template, we start by hypothesizing the existence of some smallest counterexample, and then we need to show, first, that our counterexample isn't 0, and then, if our counterexample isn't k minus 1, then it's also not k. So we hypothesize the existence of a smallest counterexample k. Then we show that 0 can't be that smallest counterexample. And then we show that if k minus 1 wasn't a counterexample, then k also can't be a counterexample, which gives us a contradiction and shows that there can't be a smallest counterexample. But if we are using this approach to prove that some property holds for all n in the natural numbers, then when we show that 0 isn't a counterexample, what we're showing is that the property holds for 0. And then if we show that k minus 1 not being a counterexample implies that k is not a counterexample, what we're showing is that if the property holds for k minus 1, then the property also holds for k. So one way to think about what we've done here is that by showing the property holds for 0, and then showing that whenever the property holds for k minus 1, it must also hold for k, what we have done is created ourselves a chain of reasoning that we can use to show that the property holds for any natural number. If we have shown this implication for a generic k, then we have shown it for every pair of consecutive natural numbers. We've shown that p of 0 implies p of 1 implies p of 2, p of 2 implies p of 3, and so on ad infinitum. So, if we have also established that p of 0 is true, then that means that everything in this whole chain must be true. And so, this way of thinking about our smallest counterexample proofs leads us to another proof template where we dispense with the proof by contradiction approach and thinking about hypothetical counterexamples and just directly attack the problem in terms of proving p of 0 and then proving this implication. This is known as proof by induction, and if you go on to take upper-level computer science classes, especially analysis of algorithms, proof by induction will be one of the most useful proof templates in your toolbox. In a proof by induction, we start by establishing a base case, proving the smallest instance of the property that we care about, typically that the property holds for 0. Then the inductive step is to prove that if the property holds for a generic k, then it will also hold for that k plus 1. And this gives us our chain of implications that shows that the property holds for every natural number. In principle, we could use any approach we want to prove this implication, and we've seen lots of proof templates for if-then statements. But we can fill in a particular proof template to help us get going, namely direct proof of an if-then statement. So most of the time, to prove our inductive step, that k implies k plus 1, we will begin with an inductive hypothesis. That is, assuming that the property holds for a generic natural number k. And then we will eventually arrive at the conclusion that the property holds for k plus 1. And we can think of this as proof template number 1, where we will unravel what the property means for k and unravel what it would mean for k plus 1, and then try to make those meet through valid algebraic manipulations. So one way to think of the connection between a smallest counterexample proof and an induction proof is that they are both setting up this same structure that leads us to a chain of implications, but the proof by induction is using a direct proof to show the inductive step, whereas a smallest counterexample proof is using a proof by contradiction to give us the inductive step. It's worth pointing out explicitly that the base case does not always have to be 0. In general, the base case should be the smallest case that we care about. And so if we wanted to prove that a property holds for all integers greater than 5, then we could show that the property holds for 6 as our base case, and then use an inductive step to show that since it holds for 6, it must hold for 7 and 8 and so on. Let's now do some examples of proof by induction. Many of the theorems that we have proven so far this semester could be very naturally proved by induction. That includes all of the things that we have shown with smallest counterexample proofs, many of the things that we've shown with combinatorial proofs, and other approaches. And for the specific things that we proved with a smallest counterexample proof, the flavor of proof would be extremely similar. Specifically, in those proofs, we said that since k was the smallest counterexample, we knew that the property must hold for k minus 1. So we were assuming the property held for k minus 1. And then we were showing that because the property holds for k minus 1, k also can't be a counterexample, so we were reasoning from the property holding on k minus 1 to the property also holding on k, and in each of the examples we did, that reasoning will look exactly like the reasoning for an inductive step if you were to prove that theorem by induction. But let's also do one more example that we haven't done before. Here we are proving a property of a real number x and a natural number n. So if we think of this as a property that can be true or false for any given n, then for a particular n, that property says that for all x greater than or equal to minus 1, this formula holds for that n. And so we're going to prove this by induction on n. So we need to start with a base case of showing that the property holds for the smallest n we care about, which in this case is 1. So here we want to show that 1 plus x to the 1 is greater than or equal to 1 plus n times x for all real numbers that meet our constraint. As usually happens, the base case is easy to show. When we plug in 1 for n, we get an equality, and so the inequality clearly holds. For our inductive hypothesis, we are assuming that the property holds for some arbitrary k. So we are saying that there is some k greater than or equal to 1 where the property holds, which means that for every real number greater than or equal to -1, we have this inequality. The goal of the inductive step is to show that the property holding for k implies that it holds for k plus 1, so we want to arrive at this property stated in terms of k plus 1. So let's put that at the bottom and try to work our way there. So now our task is to show a valid chain of reasoning that gets us from our hypothesis to our conclusion. So our goal is to show a formula in terms of 1 plus x to the k plus 1. And since our inductive hypothesis tells us about 1 plus x to the k, we can start by splitting out 1 plus x to the k, and this now gives us something that we can apply our hypothesis to manipulate this equation. In particular, we can substitute. So since this is greater than or equal to that, we then know that our left-hand side must be greater than or equal to . Now we can simplify. Then, since we eventually want to show that this left-hand side is greater than a thing in terms of k plus 1 times x, we want to aim for a k plus 1 times x on the right-hand side. And if we factor out an x from this portion, we get a k plus 1 times x term. But now we have a thing that looks like our goal plus some other term. But since our goal is to show an upper bound, to argue that this is larger, we only need to show that this can't be making the right-hand side smaller. And since k is greater than or equal to 1 and x has been squared, we know that this term must be positive. So if the left-hand side is greater than or equal to that, it is also greater than or equal to this. So we have now shown that if the property holds for k, then it will also hold for k plus 1. That gives us our chain of implications, and our base case that the property holds for n equals 1 starts the chain, meaning that we have proven that this property holds for all integers greater than or equal to 1, which proves our theorem. It's worth pausing for a moment to think about why we needed this condition that x is greater than or equal to -1. Clearly, if we had x equals -5, this wouldn't necessarily hold, because then we would have -4 to the n is greater than or equal to 1 plus n times -4. For large enough n, the left-hand side will clearly be much bigger. So clearly this property does not hold when x is too small, but that doesn't tell us where our inductive proof goes wrong if we are given an x that is less than -1. So I challenge you to figure out in our inductive reasoning where would the proof go wrong if we were to not have this restriction on x. This is worth thinking about specifically because there are a lot of little ways that it's easy to get tripped up when doing a proof by induction. So let's do another proof by induction where it will be your job to keep an eye out for holes in the reasoning as we go. For this problem, we are interested in tiling square grids using this L-shaped piece. In particular, we are given a square grid where the side lengths are some power of 2, and we want to place these L pieces on the grid such that no two pieces overlap, and we have covered all but one of the cells of the grid. Clearly, such a tiling is possible if the size of the grid is 2 by 2 or 4 by 4, but is it possible to do this for any square grid with power of 2 side lengths? Well, that's a thing that we could approach inductively. So if we want to use induction, where we use the case of k to show k plus 1, then we want to state the theorem in terms of natural numbers. And so we can think of our power of 2 side length as 2 to the n for some natural number n. And then we can do induction on this value n. So we have already shown a base case, but let's write it down. Now we need an inductive step where we assume that the property holds for n and show that it holds for n plus 1. And since we are talking about a size 2 to the n grid, when we add 1 to n, we are doubling both the height and width of the grid that we are tiling. So if we are able to cover all but one square of the 2 to the k by 2 to the k size grids, then we can arrange 4 of them such that we can place one piece covering the one uncovered square in 3 of the 4, leaving us with only one hole in the 2 to the k plus 1 by 2 to the k plus 1 grid. And so because we can use our tiling of the 2 to the k by 2 to the k to build a tiling of 2 to the k plus 1 by 2 to the k plus 1, that means that we can always go from k to k plus 1. And so for any power of 2 sized grid for a natural number power of 2, we are able to cover all but one square. So what's wrong with my proof? There are actually multiple problems with this proof by induction, so pause for a minute and think about it, see if you can figure out where my proof went wrong, or you can go back to this timestamp to rewatch and try to identify the problems. But please do not watch past this point until you have identified at least one problem with my proof by induction and made a genuine effort to find as many issues as you can. So, where did I go wrong? Well, I can think of a couple of problems. The first is that we are trying to prove a theorem for every natural number n, but our base case started from the 2 by 2 grid, where the 2 by 2 grid would be an n of 1, and so we have not proven that the theorem holds for n equals 0. As it turns out, this is an easy fix, because a 2 to the 0 by 2 to the 0 grid has only one uncovered square, so we have already tiled this grid without placing any pieces. A bigger problem with my proof is that I've made a faulty assumption in my induction. Specifically, the statement that we made that we can cover all but one square doesn't tell us where within the subgrids the uncovered square is. It might be the case, based on our inductive hypothesis, where we assume we can cover all but one square of a quarter-size grid, that the only way that we're able to cover this 2 to the k by 2 to the k grid is leaving something in the middle uncovered. And if that's the case, then our approach for building the k+1 size grid doesn't work because there's no single piece that we can place to overlap the holes in 3 of the 4 subgrids. So let's restate our induction in a way that allows this proof approach to work. Specifically, for this placing of one piece that overlaps 3 of the 4 to work, we need to have the hole in the subgrid be in the corner. So specifically, let's make our claim stronger and say that we can cover all but the top right corner of the grid. And if that's the case, then we can definitely cover all but one square, so that would imply this theorem. And if we can specifically think about covering all but the top right corner, then that will set us up to do this inductive step. So now, for the base case where we talked about n equals 1, we had a 2 by 2 grid, and we showed that we could cover all but the top right square, so our base case still checks out. But we need to modify the statement to make it stronger that we specifically are able to cover everything but the top right square. So now, because we've strengthened our base case, we can also strengthen our inductive case, and this is where it will really help. If we assume that we have a specific way of covering the 2 to the k by 2 to the k grid, specifically, if we can cover all but the top right square in the 2 to the k by 2 to the k subgrid, then we can use that to think about what happens when we're constructing our k+1 grid. Well, all we have to do now is rotate this subgrid clockwise and this subgrid counterclockwise, and now we have placed the holes in 3 of the 4 subgrids to be in the position where we can place this additional piece. And then we have the hole in our 2 to the k+1 by 2 to the k+1 grid in the top right corner. So we have shown that we can cover all but the top right square of the larger grid. We should also augment our explanation of how we tiled the larger grid. We can place one piece after rotating 2 of the subgrids. So now I believe that we have a proof of the original statement where we have fully covered the base case and where our inductive hypothesis really does imply the inductive step. While we're on the topic of proof by induction, there's one more proof template that we should talk about. Strong induction is very similar to normal induction, except that in the inductive step, we assume not just that the property holds for an arbitrary natural number k, but rather that the property holds for all natural numbers up to the arbitrarily chosen k. And here, if we can show that when the property holds up through k, that this implies that it must also hold at k plus 1, we end up with the same chain of implications because this statement on the left for k equals 1 is just the same as the inductive hypothesis. We would have that p of 0 implies p of 1. So this implication means that if we have proven our base case, then we have also proven that the property holds for 1. So that means that we have that the property holds for both 0 and 1, which means that we have the necessary ingredients to conclude that the property holds for 2, which then gives us the prerequisite to show that the property holds for 3, and so on. So, in any case where we could have used regular induction, we could also use strong induction. The same chain of implications proves the same sorts of results. But strong induction, so called because we are making a stronger inductive hypothesis, can allow us to prove some things that are harder to prove with regular induction. A great example would be the same upper bound on the Fibonacci numbers that we proved using smallest counterexample last time. When we did our smallest counterexample proof, we needed to think about both the k minus first and k minus second Fibonacci numbers in order to show a bound on the kth Fibonacci number. And likewise, if we were to show this inductively, we would need in our inductive hypothesis both the cases for k and k minus 1 in order to show that the upper bound must also hold for k plus 1. Much like last time when we proved this using smallest counterexample, we would need 2 base cases, where before we needed to show that neither the 0th nor the first Fibonacci number was a counterexample to this upper bound. We would now need to show for our base case that the upper bound holds for both the 0th and first Fibonacci numbers. And then our strong inductive hypothesis would include both that the property holds for k and for k minus 1, and so that would give us the necessary pieces to show that it holds for k plus 1. The book gives some great examples of strong induction proofs where we really do need all of these assumptions in order to show that the property holds for k plus 1. And over the rest of the semester, we'll see many more examples where induction is handy and a few cases where we need strong induction.